everyone, this is Muhammad Afur Jaman. I am pursuing my PhD in the Department of Electrical and Computer Engineering and the wavelet. And today I am going to demonstrate the Python codes in how the laser works and how the laser system needs to simulate using Python code. So in this process, I hope you guys get the docs file from Dr. Pope to how to run this code. I think it is a Windows file, a Windows docs file or something. You already get a screenshot and documents how to run this code. But however, I am going to explain it now so that you can understand how to run this code. So I just copy that steps into this screen so that I can read this and explain it to you. So first process in your computer must have to have pycharm and Python software. So you have to install that first. If you are a Windows user, then you have to copy the first link, and if you are a Mac user, then you have to copy the second link. So, for example, if you are a Windows user, then you have to copy the first link and paste it to your browser, and you will get this page. You see, this is Windows, and this is the community version. So, in every OS, you have to just install community version. So first, you just click download as according to your operating system. If you are a Mac user, just click Mac and then download this community version. And if you just click the download button, the download will automatically in progress. And after successful download, you will find like this. And then move on to the next step. And then you have to install Python in your computer. If it is already installed, then you don't need to install it. And if it is not, then you have to install it first. Just copy this link. You see this link. Just copy this link. Copy this link to your browser, and you will find this page. If you are a Windows user, then just click this button. And if you are a Mac user, just click Mac OS, and then you will find like this. And download Python software according to your operating system, and just click download. And it will automatically download like this, and you will find it in your machine like this. And then just click install. So you have to first install these two software in your system, in your operating system. Just click it and install it. After successful install, just search for pycharm in your task manager or app manager and open the pycharm app. And this is the UI for pycharm. You see, at first you don't find like this window. You have to first create a project. So to create a project, just click File. You see the left side of the pycharm window. You see File. Just click the File, and you will find a new project button. Just click New Project button, and you will find you will have to put a name. You can put it as a, for example, laser. Just create. And if you click this create, you will find like this page. So you have to find the file name called main.py, and you just need to find it and just open it in pycharm and select all and just paste the code that I had already, I mean, the Dr. Folk already given to you through ELC or email. Just paste that code into this file and save it. So it is almost done. And just you have to wait for a few seconds, because in this code I have already used some packages that is related to fiber optic and laser. I mean, some packages that is already built on fiber optic and laser topics, and just need to install that packages in Python. And there are the two packages. The first package is Matplotlib. It is used for plot the data. It is quite commonly used in Python to plot data. And the second one is Lightpipes. It is fully on fiber optics and laser package that is built on Python system. You just need to install that. There's two packages. So to install that packages into your pycharm, you just need to go to terminal. You see the bottom, the terminal here. Just click it. Just click it. You will find like this. So to install a package in Python, you need a command called pip install. So I just need to install Matplotlib. So I will just copy this command pip install Matplotlib. You see, pip install Matplotlib and just paste it. You see, like this. You will just paste it into your path. You see. Oh, this is the second one. Yeah. So you just need to copy. There's two commands: pip install Matplotlib and pip install Lightpipes, like this. So just copy this command and paste it into your terminal. You see, this is the terminal. This is the path of your project, and just install pip install Lightpipes. Just enter button. And as my system has already installed, so it gives a verdict requirement already satisfied. But in your case, you will find a bar. That means the download is processing, or download is going on, or download is almost complete, like this. So you just need to copy these two commands and paste it into your path and just type enter. So you see, I'll make you see this. You see, you can install Matplotlib, enter, and you will have to install the automatically that code, that packages into your system. And then the second one, Lightpipes, and these packages will be installed. So as my system has already installed the packages, so it gives a verdict requirement on it. Otherwise, I will must have to see like this, the download is going on. Like. So it is done. The system requirement is ready, and then you just need to click run button. So you have to run this, you have to find this here. You'll see like here first a people button, like then name, and then you find a arrow here. So as I'm sharing my screen, so I just already clicked on this arrow, and it is converted into a loop. Otherwise, you will see a arrow here. So just this is the run. You can see the run main here. So just click it, and you will find a window like this. You will find a window like this. So this is the real-time simulation of our laser system. So your task is to just move the button from left to right and change the parameter of the system and analyze the data. the change of power, the change of Gaussian shape, the change of power here. You see, I have set the reflectivity to 0, so that's why there is no Gaussian thing. So just change the reflectivity. You see, there is no change because this system is quite slow. The cell response is quite slow here. So you just need to wait for a few minutes of time to get something. So here there are 7 parameters here. First parameter is aperture. You just need to remind this. First is aperture, second reflectivity, mirror radius 2. That is, there are 2 mirrors. I will explain why there is 2 mirrors. And then another is resonator length, another is gain. This is alpha, just remember this. And this is Eigenmode like TE01, TE02, TM01, TM02 like this. So let's move on to the main code part. So the code is quite long, but you don't need to worry because it is a real-time simulation. So that's why I just put some codes or plotting the data in real time. But the original main code part is too small. So at this part, I just import some packages that I have installed in Matplotlib and Lightpipes. This package contains some header files or some more packages inside this as a zip. So I just need to import the packages to use it in my code. So let's move on to the main part of the code. You just leave it here. Yeah, I just put all the comments on the other side of the code so that you can read the comment to understand what is in the meaning of this code. So in the basic laser system is in our experiment is basically a fiber coupled loop laser or ring laser. So you have to build up a fiber system and amplifier system to generate a laser, and it must be in a loop. So you see, first you have to generate a power source. So I will explain later why I divide this part into different systems. Because first you have to generate a power source, and then you have to amplify and up to a certain gain. So this part will give you the certain gain included with the power system. Then you will find an amplifier system here to put more gain on your system, but it is an optical gain. And then you have to apply some filter. Then you have to apply some coupling ratio. Here, coupling ratio means you need to split your optical power into different percentage and pass it into different fiber. So that's why we have to tell the coupling ratio. Then there are some attenuation to increase or decrease the intensity of the optical system. And then this power loop will feed back to your original power system again. So this is called fiber coupled ring laser. So this is the simulation of Python. This is the simulation of fiber coupled ring laser using Python source code. So why I mention this, because there's in every part, this part, there are some parameters. There are some optical parameters. So you have to consider those parameters and change those parameters, and you have to analyze the system. So you see, there are 7. You see the aperture diameter, reflectivity, mirror radius, resonator length, gain. So those are the parameters that is related to these subparts. So you have to change those parameters. To change this parameter, you just need to drive your mouse left to right on this button and change it into a certain value so that you can get something. So that you can get something here. So I will explain currently my PC hangs for a few seconds. So it is not given real time data. I will restart it later and run it again to give you a real time view. So that's the 7 parameter you need to change. So in real time, I will try to display this in real time. So I need to store this value into a variable so that I can use it a quite number of times. So you have to just declare your variable as global so that until you close the pycharm, it will hold the value for you. This is the meaning of global. So this is F. This is F for the initial intensity, the initial power that is given to your laser source, and this one is for radius. You have used a mirror because to increase the gain in this system we have used a cavity resonator, and inside this cavity resonator there are 2 mirrors to reflect the light. So this mirror has an aperture value, so you have to store the aperture value. So W0 is the aperture value, and F1 and F2 are for the radius. And then you have to apply some semiconductor optical amplifier. So you just need to tell the reflectivity and convert your intensity. The amplitude, power amplitude into FFT. We are transformed into your semiconductor amplifier, and then you have to filter your system. Then you have to filter your system using a filter, and then you have to split the optical power into a certain ratio, for example 90% or 80%. So you have to just input the value 0.8. That means 80%. That means your optical power will be divided into 80:20%, because 0.08 0.8 means 80% into 20%, and then there are some attenuation applied as a parameter, and so that we can analyze our laser system quite well. And then in this feedback is used again and again quite number of times. So at first we need to generate a random intensity, the power source. So let's move on. So to get the data from this page, to get the data, we just use the method named scale underscore something dot get. That means we will get data from that point. So for example, this one, you just move this button. So this is the first point. So you will just need to find this like scale f1 dot get. It will give data from this button. And for this is for scale underscore f2 dot get. It will give the second point. So you need to just take the parameter of data from this button. You just need to write a scale method. So these are the 7 parameters that I took from the UI by changing the button from left to right like this. So So let's move on to the main part. As we described earlier, this system needs some random intensity. So this is for the random intensity function. So just call this method, and this method needs 3 parameters. First is the value, that initial power value, and second one is some seed. Seed means it will generate some random data in a certain range. If it is, for example, it is 10 to the power -8, that means it will give you some random data from 0 to 10 to the power -8 in between. And this is the random noise. So I took it as a noise because I took the current time as a random value, as a random noise. For example, currently it is 10 p.m. So it is 10 p.m., 10:20, 10 p.m. That means 10 hour, 20 minute, 20 seconds. In the whole data, time data as a random noise. You can put another random data as well. So don't bother about the order here. Here I describe an ascending here, but in real life code it is in descending. It is reverse order. So don't bother about the order. So this is the intensity. Yeah, this is the intensity. So this is the seed. This is the seed, and this is the noise. This is the noise. And then, as you can see, I need to apply some gain using resonator. So I need to apply some mirror something. So to get mirror something, you need to apply some aperture here. So just call this, and this W naught is from the this structure, the first button of the UI. So W naught, and just apply the apply this aperture into this random intensity that we earlier. And at this point, we have applied the resonator gain. I mean, we are at this point. We're at this point, and now we have to apply some optical gain. Until now, it was like electrical something gain, but now you have to apply some optical gain. So to apply some optical gain, this is semiconductor optical, that means SOI. But this method has some requirement. It needs a field that has FFT. That means it asks for some FFT field. So to get FFT field, you need a forward method. So first you need to apply forward method to convert your field into an FFT field. But this FFT field asks for some lens method for idea of lens medium, Gaussian lens medium method. So then your power system or your intensity system must have to convert a lens system first, then into an FFT system, then into a semiconductor optical amplifier system. So these two are actually the requirement for the SOA gain. So as we use a random intensity gain and random intensity, cavity resonator gain. So we need to measure the amount of intensity first. So this intensity will provide you the measurement. Just it will give the measurement how much intensity is created right now. Because we are analyzing the system in real time. So in 2 seconds ago, the intensity, and now it might be different. So yeah, we have to measure in every second. Yeah. So that's why I just call this method. This will return you the current intensity. And then convert into a Gaussian lens medium. as a requirement of forward, and forward convert it to FFT, and there is this FFT medium is given to the SOA system, and SOA system will give you the actual optical gain. So if you are not satisfied with the SOA, the SOA system, then you can repeat this method with 2 times, 3 times, more times. This is the repetition of the process. And as I was not satisfied, then I just applied it for too many times. You can say I use 2 SOA system. So after applying SOA, I just use a filter. So here is the random filter. Yeah. So now our current data is in FFT system. So you have to apply an FFT filter here. So I just apply a FFT filter here. First apply a FFT filter, then apply a Gaussian filter with the aperture W0, and then we invert the FFT to get to measure the intensity, because you can't measure the intensity until it is reverse or inverse FFT. So the inverse FFT here, and then apply intensity method to measure the current right now intensity of the system. So it is the current intensity of the system. And then we have to apply some attenuation. So this method, inter-attenuation method, will apply some attenuation, because in fiber system there are some insertion loss or something. You need to minimize the loss or gain of something, and you have to apply attenuation in a certain way. And then if you just find out the power of the system in milliwatt or certain parameters, and this is the equation for power. And as this system will provide the real-time simulation, so I need to save all this parameter into a global variable, so that until the end of the program I can get whatever I want. So I just use an append method here to save this. And this round trip is for the Windows side, because you see this is the last point of the real-time simulation, the 500. Actually, it defines the time. So our system can only describe 500 data, and after this 500, it is the previous data. So until 500, it does increase the number of iterations so that you can get the value on real time. And then the plot the data. So in plot function, if the first plot is depicted the cross section of the fiber. If you see inside the fiber, you will find laser beam like this, the first plot. The second plot is the power or form of the laser. It will give you a ball shape or parabola shape. This shape is called Gaussian shape. So every laser have to have this kind of shape, like Gaussian shape. And this is the real-time power spectrum my system has. So I can quit this for a few seconds and just wait for a few seconds. Let's click here. So I need to add my window so that you can see Okay, this is the window, a real-time window. You see the power is increasing, the Gaussian Gaussian shape is changing, here the value is changing. So that's why I'm telling this as a real-time simulation of the laser. So you just need to wait for past few seconds. If you turn on the laser system, it needs some time to get a stable laser beam. So you just need to wait because the system response is quite slow. So you just need to wait for a few seconds. So now the target of this simulation is that you need to change those parameters here. You see the aperture diameter here. You just need to change and wait for four or 5 seconds because my system is also the response is quite slow. And then change the reflectivity. And you have to see the change of the laser in the fiber medium, the cross section of the fiber. You will see like this laser. And this is the Gaussian, the mathematical form of the laser, how the mathematical shape of the laser looks like. This is the Gaussian form. And this is the power, the real-time power change, how much effect it input into the system after changing this parameter. See the real-time change. And then I have just test this. So you just need to a note or take a note and for example, aperture diameter for aperture diameter 8.2, reflectivity 0.97, mirror 200, mirror to 500, resonator 30, and gain 0.067, and my power is 8.94, or special gain is like this, or the mean 0, and the standard deviation is like this, and the variance is like this. So you just need to wait for few. You just need to wait for few seconds to get a. You just need to wait for few seconds to get a stable one, and you can change the Eigenmode. Eigenmode means the TETM mode. I think you have heard about this TETM mode. PE01, PE02, so you can change this. Just click on the upper part, change this, and click Eigenmode. If it is applied, then you will see injected Eigenmode. Number type goes 01. I have applied T01 mode. So the power to change, you have to wait for a few seconds to get a stable laser source. Yeah, you see the power is changing, but the response is quite slow. So you have to wait. So this is my first test for aperture. This, reflectivity this, mirror this, resonator length this, gain this, and eigenvalue for this. I have found power 0.02 milliwatt, special with 988.99 millimeter, mean this, standard deviation this, variance this. So these are the simulation, and you will find like laser mode here, 01. And if you cut the cross section of a fiber, you will laser mode. You see now it is stable. Just at least you wait for 7 to 8 seconds to get that result. So this is the first part, the cross section, fiber cross section, and this is the second plot. In this second plot, I just do one thing. Your system is ready, but the problem is because the laser comes from a physical material, I mean semiconductor material. So that's why it gives you the Gaussian ball shape. But in code, I could not generate them because I don't have any physical medium to generate data. That's why I need to apply a Gaussian type of mathematical form so that I can get the power into a Gaussian form. So I just use multivariate normal and the power distribution. These two methods is used to convert my power into a Gaussian form. The second one that I have seen, that you have seen here. You see, this is a Gaussian form. Let's convert it and plot it. And it gives the real-time simulation. Yeah. You see the change. So here my window size is 500. So after 500, it will erase the back 500 part will be erased, and the recent 500 will be shown on this graph. That's why I use round trip. If it is 500, then I just erase. You see, yes, it is 0. Yeah. So in summary, that's the overall system. You just need to run a test for different parameter, for different these 7 parameter. You just need to observe this and this spatial width means this width, and this part to this part with this part spatial. That's the overall. In summary, at first you need to go through the docs file that Dr. Mabel is already shared to you, and then open my code. You will find some step also, because if anyone missed the docs file, then he can be successful to run the code. I just put something here, and then do what I already said to you. Thank you guys. Have a good day.